Bismillahirrahmanirrahim. Dear students, today we are going to start chapter number same 16 and the lecture number is 39, grade 12, cis and trans geometrical isomerism. Cis and trans or geometric isomerism. Previous we done all kinds of the isomerism and stereoisomerism. In the stereoisomerism, we done the optical isomerism, then geometric or cis and trans isomerism. Now, in the geometric isomerism, the restriction in rotation about the double bond or about single bond in cyclic compounds. In the geometric isomerism of alkenes, there is a double bond between carbon and carbon atoms. And you know that in the double bond, there is one sigma bond and one pi bond, and there is a sp2 hybridization. In the alkenes, there is a sp2 hybridization of carbon-carbon double covalent bond. There is one sigma bond and one pi bond, already I told you. The sigma bond is formed by the straight arc end-to-end overlapping of p and p orbitals, and sp2 hybridized atomic orbitals, while the pi bond is formed by the overlapping of parallel unhybridized atomic orbitals. So this presence of pi bond lack each mobile in one position. The two carbon atoms have double bond and the four carbon atoms are attached, lying on the one plane, and their position of space are fixed. The rotation around the carbon-carbon double covalent bond is not possible because rotation would break the pi bond. So the pi bond is not going to be rotated. If it is going to be rotated, it is going to be broken down. In the stereoisomerism, you done this, there is rotation possible. So if there is a rotation, then there will be a breakage. Just like I am giving example, these are the two wooden pieces. These are the two wooden pieces, and you have to put one nail. You have to put the nail by using hammer. So if there is a one nail, it can be rotated. Rotation is possible if there is a one bond, sigma bond. But if you put one nail here and other nail here, so rotation is not possible. These two pieces of the wooden cannot move. So if you are going to try to rotate, it will be broken down. So that is why in between the two carbon atoms, if the double bond, one is sigma bond and the pi bond, so rotation is impossible. Rotation is not possible between the two double bonded carbon atoms. So that's why in your book written that rotation around the carbon-carbon double bond is not possible because rotation will break the pi bond. Same example which I gave you, if there are two nails connected by the two nails of two wooden pieces, that if you are going to start rotation, they will be breaking very hard. Rotation about pi bond is not possible because it would break the pi bond. The rotation about pi bond is not possible because it would break the pi bond. This restriction of rotation about the carbon-carbon double covalent bond is responsible for the geometrical isomerism in alkene. So, dear students, what's going to be here? Rotation. About pi bond is not possible because it would break the pi bond. I gave you examples of two wooden pieces. That's like this restriction of rotation in alkenes, this restriction of rotation in alkenes between carbon-carbon double bond is responsible for the geometric isomerism. This is a popular analogy of situation based upon two bonds, just like I told you, two nails you are putting in the wood. So these two nails prevent the rotation of the between the two cardboards or two wooden pieces. So dear students, if you have an example of two butene, according to geometrical isomerism, the organic compounds having carbon-carbon double covalent bond, same molecular formula, same structural formula, but the alkyl groups attached with the carbon containing double bond, they have a different position. They have a different, just like I told you, the two butene, this is a carbon, double bond, this is alkyl group, this is alkyl group, 1, 2, 3, 4 hydrogen, and this is also two butene. And I will draw another one, carbon double bond, alkyl group, and alkyl group here. So this is the hydrogen and this is the hydrogen. So dear students, you are seeing that there are both two butenes, but you are seeing here alkyl on the same side. On opposite side different, alkyl and hydrogen and alkyl and hydrogen up. You are seeing two alkyl groups same, and down you are seeing the two hydrogen atoms same. And in this case, these two alkyl groups are going to be opposite side same and hydrogen same. On the upper side, alkyl group and hydrogen, and downward side you are seeing alkyl and hydrogen. So if the same side is here, this same side, opposite different, we call cis. This is a cis butene, and this is called a trans cis-2-butene and trans-2-butene. So this is the geometrical isomerism for the cis-2-butene, and this is the trans 2-butene. So these two structures of 2-butene are referred as geometrical isomerism and distinguished from each other by the term cis and trans. Their name is same, molecular formula is same, even structural formula is also same, but the alkyl group and hydrogen, they are differently arranged with the carbon containing double bond. So the cis isomer is the one with two similar groups on same side. Methyl alkyl group same side, hydrogen same side, and trans, these are opposite sides. The cis isomer is one in which two similar groups are on the same side of the double covalent bond. The trans isomerism is that in which two similar groups are on opposite side of the double covalent bond. So this type of isomerism is referred as called cis-trans isomerism. So I told you these geometrical isomerism are also called stereoisomers because they have the same structural formula but different spatial arrangement of the atoms. So the conversion of cis isomerism to trans isomer vice versa is possible only if either isomer is heated at high temperature. So this is going to be converted into this one. It is only possible that if you are going to heat this system at very high temperature, then interconversion is going to be possible. This will need about 62 kilocalories per mole. 62 kilocalories. 62 kilocalories per mole is needed to break this one. Pi bond, so that rotation about sigma bond becomes possible. Then it's possible, otherwise no. So upon cooling, the reformation of pi bond can take place in the two-way giving mixture of cis and trans isomerism. The trans isomerism are more stable than that of the corresponding of the cis. Trans isomerism. Trans isomers are more stable than cis isomers. Trans, carbon opposite side. This carbon containing double covalent bond, single bond carbon alkyl group. This carbon double covalent bond, and there is a carbon. But here you see this carbon double bond same side. So that's why also in your book it is written that this is because in cis isomerism, this is cis same side. The bulky group on the same side, carbon, which are attached to double covalent bond, bulky group same side of the double covalent bond. The steric repulsion of group makes cis isomerism less. Steric repulsion. There is repulsion between this. Steric repulsion make the cis group less stable. And bulky group are far so opposite side of double covalent bond. That's why more stability is here. The geometrical isomers have different physical properties and chemical properties. They can be separated by conventional physical techniques, by the fractional distillation because their boiling point is different, gas chromatography, and etc. Now students, there is a very important point that all alkenes do not show geometrical isomerism. All alkenes do not show the geometrical isomerism. Where it's possible, geometrical isomerism is possible only when each double bond carbon atom is attached with a two different, this carbon two different attached, this carbon two different, this carbon two different, this carbon two different. If I put here hydrogen, then the cis trans or geometrical isomerism will not form. Same group attached with the same carbon, then geometrical isomerism is impossible and cannot be formed. So written here, dear students, only when each double bond carbon atom is attached to different atoms of the group. Two different atoms of the group. Only possibilities here. So if you have example, propene. Like this one. This is the propene. Carbon, double bond, this is the carbon, and carbon double bond, so in the propene, one carbon has one hydrogen and same carbon has another hydrogen. Yes. And this carbon has a hydrogen and also CH3 already desired. This is propene. So there are two same. This carbon atom has attached the two same hydrogen atoms. So there will be a no cis trans isomerism. There is no geometrical isomerism for the propene. Suppose we have 3 hexene. Carbon double bond, one, two, three, or 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So these are 3 hexene alkyl groups, 2 alkyl groups, CH2CH3, CH2CH3. 2 different groups are here. So this is cis 2 3 hexene. And if you are going to put alkyl group here and hydrogen here, they will be opposite, and this will be called trans 3 hexene. So there is isomerism in the opposite side, cis 3 hexene and trans 3 hexene. Yes, you can see in your book also there is, and there is another cis and trans isomerism in the carboxylic acids. Butyndioic acid. Butyndioic acid. HCOO. Like this one. So if you are going to write cis-trans isomerism. This is the carbon, this carbon, and this carbon, they contain double covalent bond. Hydrogen is there. So if there is a hydrogen, the same hydrogen I am writing here, the same. This is the hydrogen I am writing here, same. And this is a carboxylic functional group. This is a carboxylic functional group. This is a hydrogen and hydrogen. Okay, there is a double covalent bond, carbon again. So if you put COOH here and hydrogen is here, this is called a trans. This is called trans. Cis and trans. This is a trans. And this trans butene dioic acid is called a fumaric acid. And melting point is 130 degree centigrade. This is the trans fumaric acid. And if like this one, carbon-carbon double covalent bond, both are same side, like this one. So here, two bulky groups are same side and hydrogen same side. Here, different side. This is called a cis. Cis butene dioic acid, and this cis butene dioic acid is called a maleic acid. What we call maleic acid, and this maleic acid has a melting point about 288 degree Celsius. So when the two bulky groups are on the same side, these two bulky groups are on the same side. So students, that's why it has a melting point more than that of the bulky groups are on the opposite side in the form of trans butene dioic acid or fumaric acid and cis butene dioic acid or maleic acid. This is a maleic acid and this is a fumaric acid, and they have a formation of cis and trans. Students, the geometrical isomerism are also possible in the cyclic compounds. In the cyclic compounds, there is also possibility for the formation of cis and trans geometrical isomerism. So suppose if you have a cyclopropane, this is a cyclopropane. If the alkyl group is attached here, methyl group, and there is the one hydrogen, okay, this is hydrogen attached here. We satisfy the reduction of carbon, there is carbon, there is carbon, there is also carbon. And if you are putting also alkyl group here, and there is also hydrogen here. So dear students, this compound is called 1,2,3,1,3-dimethyl cyclopropane, 1,2-dimethyl cyclopropane, 1,2-dimethyl cyclopropane. So two same side. So this is called a cis. This is a cis arrangement. And if you write like this one, here same alkyl group, hydrogen. But in this case, if hydrogen is here and alkyl group is here, this is called a trans. Like this one. So this is a cis 1,2-dimethyl cyclopropane, and this is called a trans 1,2-dimethyl cyclopropane. But if the same groups are attached, like this one. So this will not show. One dimethyl. This is a one dimethyl cyclopropane. One dimethyl cyclopropane will not give a geometrical isomerism because two same group attached with the same carbon atom. So due to this reason, it does not form a geometric isomerism. So one dimethyl cyclopropane, no geometrical isomerism are possible in this compound. There are no geometrical isomerism, and here geometrical isomerism are possible because different groups are attached different carbon, alkyl hydrogen, alkyl hydrogen, alkyl hydrogen, and alkyl hydrogen. There is formation, but hydrogen, alkyl, alkyl group, there is a no geometrical isomerism. There is no. No geometric isomerism. In this case, no. So, dear students, this is about the cis and trans geometrical isomerism. So, students, we completed the structural isomerisms, and I told you 5 types. And then I completed the stereoisomerism. Stereoisomerism has 2 types. One is called optical isomerism, I told you, and this is about the geometrical isomerism and cis-trans isomerism. And cis-trans isomerism is a form in the open chain hydrocarbons with the containing double covalent bond between them, single bond and pi bond. And the very important thing is that rotation about the pi bond in the carbon-carbon double bond containing is not possible because it would break the pi bond. So that's why a cis-trans isomerism is possible in this case. The restriction of the rotation about the carbon-carbon double bond is responsible for the geometrical isomerism, and these can be interconverted into other upon the very high strong heating. Strong heating can be converted the cis and trans isomerism in the both cases. Cis isomerism, which contains similar groups, are on the same side of the double covalent bond containing carbon-carbon atoms, and the trans isomerism is that which similar groups are on the opposite side of the carbon-carbon double covalent bond. Already I told you in the cyclic and open chain also both. So, cis isomerism are more stable than that of the corresponding of the trans isomerism. Trans isomerism more stable than that of cis isomers. This is because cis isomer, the bulky group, are on the same side of the double bond, and the steric repulsion of the group makes this isomerism less stable than that of the trans isomerism. That because the bulky groups are formed, they are on the opposite side of the double covalent bond. There will be a very less steric repulsion between the carbon-carbon atoms. So due to this reason, the cis isomer is less stable and trans isomerism is more stable. So these examples I gave you for this one. You have to see very well, dear students. So we completed the topic of the isomers. So these examples, quick quiz are here, and you have to solve all these. Which of the following compounds show geometrical isomerism? 2-butene, 2-methylbutene, 2-pentene, and 1,2-dichloropropan. So please do this one very carefully and show that if there is a geometrical isomerism or not. And the hint I am telling you that is given here. If the two different groups are attached to the same carbon atom, they will give the geometric isomerism. If the two same group, hydrogen atom, same carbon, alkyl group are same carbon, halogen carbon, same, so there will be no geometric isomerism. So due to this reason, it's very clear that when you are going to draw the structures of the geometrical isomerism, must see the carbon-carbon double covalent bonds. These carbon must contain different groups. So dear students, in the next lecture, inshallah, we are going to start the alkynes, triple covalent bond containing hydrocarbons. So thank you very much, and you have to concentrate this.